Okay, recording is on. Okay. Okay, so we'll start this lecture. Okay. Okay, so welcome to all of you. So today we'll start the introduction part of this optimization methods for mechanical design. Okay, so what you see here is the syllabus of this optimization methods for mechanical design. This is exactly the same as the MTech syllabus which we teach as an elective. Okay, so it consists of various parts, and I will briefly describe. Okay, first is introduction to optimization, basic concepts, convexity, and various type of optimization and all that. So this will be done. Then single variable and multi-variable optimization, constraints and graphical methods and all that. Okay, then non-traditional algorithms like genetic algorithm, simulated annealing, etc. And also multi-objective optimization. Okay, these things we will do. And in the end, we'll do some MATLAB toolbox examples, okay, for optimization. And this thing we will not do, probabilistic method of optimization, because that is too complex and it is not easy to implement for engineering projects. Then you can use these textbooks. Most of my materials is obtained from this 1, 2, and 3 and 4. Okay, all these books. And some materials I have taken from internet also. Okay, from other sources. So I will share the lecture slides after 2-3 days. Okay. When every topic is over, I'll share the lecture slides. So first we'll go to introduction of optimization. So what is meaning of optimization? It comes from Latin word called optimus, which means best. So optimization in engineering means finding best solution to a problem within certain limitations. Okay. So what is best solution as per optimization? So as per optimization, best solution is either to minimize something or maximize something. That is the only thing it will understand. So examples of minimization is that to have least weight, least cost, shortest time, etc. Example of maximization is to have high strength or high stiffness and things like that. Now you can also have combinations of the above two. Okay, for example, you can have least weight and high strength. So that is called multi-objective optimization. Least weight and high strength. Actually, multi-objective optimization is made up of conflicting objectives. So least weight and high strength are conflicting objectives, because when you try to minimize the weight, you are reducing the materials and you will not get high strength. So this type of conflicting objectives is called multi-objective optimization, that we look at in the end of the syllabus. Then how do you represent best solution? It is represented by a objective function. And this objective function can be either maximized or minimized. Okay. So one example of objective function is minimize f of x, y, z. So if x is the length, y is the breadth, z is height of a body, then f of x, y, z can be the volume. Okay. That is to minimize the volume. So this is an example of a objective function. And I earlier mentioned optimization means obtaining best solution subject to some limitations. So these limitations are called constraint equations. Okay, so so what is the meaning of constraint equations? So some examples of constraint equations are shown here. So one is type of constraint equation is called inequality constraints. That is, you don't allow a value to increase beyond a certain value. So one example is that stress in a body should be less than or equal to yield stress. So that is represented in the notation like stress minus yield stress should be less than or equal to 0. Okay, then another type of constraint is called variable bounds. For example, thickness T of a tube Okay, that should be between 5 mm and 10 mm. So that is another example of a inequality constraint. It is called variable bound. Then third example is equality constraint. For example, if x is the breadth and h is the height, then xy should be exactly equal to 1. So if say b becomes b by 2, then h should be 2h. So only that type of combinations will be allowed by equality constraint. So the objective function has to be maximized or minimized subject to these constraints. That is, you should choose the values allowed by these constraints. And typical optimization example, this is just for your visualization. Minimize this objective function, which is a function of a single variable. So it may be density of a body or volume of a body. That is, x is the single variable. And what is the constraint is that x is allowed to vary between -5 and 7. So it is a variable bound type of constraint. Okay, so here we already saw f of x is the objective function. This x is the design variable. Okay, so x can vary within certain ranges. In this case, -5 to 7. So how do we solve this problem? So at this stage, we have not studied any mathematical method, so we will try to plot it graphically. Okay, so the basic method is to simply plot the objective function and see where maxima and minima occurs. So let us plot this objective function. So I have plotted this objective function. So this is the objective function. Okay, within the range of -5 to 7. So x is there on this x-axis, and f of x is there on the y-axis. So if you look at this plot, you can see several complicated things. There is a global minimum and global maximum and a local maximum. There is a global minimum and a local minimum. Okay. And there's something called a saddle point. Okay, so here you can see that the objective function can have many peaks. So if you want to do maximization, your algorithm should pick this global maximum. It should not pick the local maximum, because local maximum gives a smaller value of the objective function. So if you are doing minimization, your algorithm should pick the global minimum, which should not pick the local minimum. And that's another point called saddle point, where the slope is 0, but it is neither global minimum nor local minimum. Okay, so let us see the importance of these points. Okay, then another important thing is that if you use a optimization algorithm which is not well designed, it will get stuck in the local maxima or local minima or the saddle point. So suppose we want to solve this maximization or minimization problem mathematically instead of graphically. How will you do it? We have already studied this in the engineering mathematics. You have to set the first derivatives to 0 and solve for x. So they will give the points where slope is equal to 0. So suppose this is the objective function. So first derivative will give all the points where slope is equal to 0, like this. And then you have to check if it is maxima or minimum. So you have to check second derivative. So at minima it will be positive. Okay, second derivative will be positive. In all these minimas it will be positive, and in the maxima second derivatives will be negative. And most important points are global minimum and global maximum. And good optimization algorithm must find global minimum and global maximum without getting stuck in the local minimum or saddle point. Then let us look at a more complex example, which is a function of two variables. Okay, so here f of x is the function of both x and y. So you will get a surface. F of x will be a surface. and some regions are there. X is allowed only between 0 to 10 and Y is also allowed only between 0 to 10. So let us plot this f of xy versus x and y. Okay, so you will get a objective function surface. So f of x is actually the height above the xy plane. Okay, so you can see that this is the typical objective function plot of complex engineering problem. There will be a lot of local maximas like this. Okay, lot of local maximas and one global maximum. So here the optimization algorithm has to correctly pick this global maxima, and it must not get stuck in any of this local maxima. So this is some particularly challenging type of optimization algorithm. The important points: f of xy will be a surface, and there is large number of maxima and minima. So where does minima occurs? Minima occurs here at the bottoms. Okay, all these are the minimas. Okay, so you have local minima and global minima also here, although you cannot see it properly from the top. Okay, so okay, large number of maxima and minima. There will be global maxima and global minima. The algorithm has to search the entire XY domain to find the global maxima. Okay, and to solve this type of problems, sophisticated optimization algorithms are required, like genetic algorithm, particle swarm optimization algorithm, etc., has to be used for this type of complex problems. So, how do you solve this two-dimensional problem? Mathematically. First, you put the partial first derivative to 0, partial second derivative to 0. Then you will get all the points where the partial slopes are 0. So you will get all the points where the maxima is there and minima is there. Okay. Then how to check if they are the maxima? For that, you have to check this second derivatives or the SCN matrix. So del squared of f of xy should be less than or equal to 0 for maximum. Okay, so all this x1, y1, x2, y2, x3, y3, which you get from this slope equations must be substituted in this second derivative equation. So you have to check if they are less than 0. If they are less than 0, it is maximum. Okay, so this thing is highly important. So what is the general statement of optimization problems? That is, what all things you have to specify to get the proper optimization problem. Okay, the first is that you have to say the vector of design variables. Okay, let x equal to x1, x2, x3 be the vector of design variables. Okay, for example, if I want to minimize volume of a beam, this will be length, breadth, height. Okay, so that has to be defined. Then x is a subset of real numbers. So we are not dealing with any imaginary numbers. X is a subset of real numbers. So x can be integer, positive real numbers, etc. Okay. A negative number can also be real number, but we don't take negative length, breadth, height, etc. Okay. So you have to specify. Okay. So x is subset of real numbers. Okay. Then you have to specify whether you want to minimize x or maximize x. So in this case, we say we want to minimize x. Then you have to give list of equality constraint. Okay. So h1x, so according to optimization notation, h1x represents the alphabet H represents the equality constraints and G represents inequality constraints. So h1x is equal to a1. That is the first equality constraint. S2x equal to a2 is the so second equality constraint, etc. And then you can give P inequality constraints. That is G1x is less than B1, etc. So what is the meaning of this when we solve problems? You will see. But in order to fully specify an optimization problem, you have to give all this information. So when you do the MATLAB toolbox, when you want to solve a problem, you have to give all these things. You have to give vector of design variables. Then you have to type in the objective function. You have to give the list of equality constraints. You have to give the list of inequality constraints. Okay, then another highly important thing is duality principle. What is duality principle? Minimizing f of x is the same as maximizing minus f of x. Okay, so this is f of x and minima is x star. Minima is x star. Okay, so now I take minus f of x. Okay, so maxima of minus f of x is there, and that is also giving same solution x star. Okay, so this is convenient for certain optimization algorithms. So some optimization algorithms will do only minimizing. So there, if you want to do maximizing, we have to take the negative of the objective function. And if you give that to the algorithm, it will do what we want. Okay. Then another thing is that subject to continuity and non-zero values, it is also equivalent to maximizing 1 by f of x. Okay, so this is f of x. Minimum value is x star. This is 1 by f of x. Minimum, the maximum value is also x star. But one problem with 1 by f of x is that sometimes f of x may become 0 and you may get divided by 0. So this minus f of x is more preferable to use the duality principle. Then another highly important concept is feasible design and feasible region. Okay, it's also highly important. So design variables, okay, optimization design variable like length, breadth, height of a beam can take many values in the set of real numbers, but many of them violate the constraints. For example, a beam cannot have any values of length, depth, and width. Okay. So some of these values will lead to high deflections and high bending stresses. So those will be violating the constraints for deflection. For example, we may give a deflection constraint that deflection should be less than or equal to 2 millimeters. And we may give a bending stress concern that bending stress should be less than or equal to 300 MPa. So any values of length, breadth, depth that violate those constraints will be out of the feasible region. Then also length, breadth, height cannot be negative values. So there must be only positive values. So negative values and other values which give high deflection and high bending stresses will be, it is said to be in the infeasible region because it violates the constraints. So design variables which satisfy the constraints is called feasible design, and they are located in the feasible region. So feasible design is any combination of L1, B1, H1, or L2, B2, H2, or L3, B3, H3, which satisfies all the constraints. So if a beam is satisfies all the constraints, then that beam will not fail. Okay, its deflection will be within certain limit, its bending stress will be within a certain limit, so that beam will not fail. Okay. So now let us see some diagram of this. So okay, this is the same thing. What I wrote here, the same thing I already explained. Here we can graphically see the things. So let x be the breadth of a beam, y be the depth of a beam. This is a 2D chart, so I can show only two variables. Okay, so this region is called the feasible region. So all the beams, all the combinations of y and x within this feasible region will have bending stress within the limit, deflection within the limit, and so on and so forth. So all these XY values will give safe beams. That is, they will not break. But only one of these values will give the optimal beam. Optimal beam means beam with least weight. Okay. So all these beams are okay. All these other XY values are okay because they don't violate the constraints and the beam will not collapse. But out of this, only one value will be the optimal or best design. So that is what we have to find with the algorithm. Okay. Sometimes you can have multiple optimal beam results if the object satisfy the same values. Okay. Those things we'll check later. Okay. So then another thing is that if the constraints are too many, feasible region becomes small. Okay. Okay, suppose you have too many constraints, that the deflection should be less than 1 mm, bending stress should be less than 300 MPa, shear stress should be less than 200 MPa, first natural frequency should be more than 5 Hertz. Then if you add on more and more constraints, the feasible region will become small. That is, you don't have much choice. So, okay, so this is what I said. Any values of X, Y, Z which are in the feasible region are called acceptable design because that beam will not fail. Then optimum design is the best among the feasible design. That is what we have to find with the optimization algorithm. Okay, so now let us do some quick example on visualizing the feasible region. Now, suppose I have two design variables, x1 and x2. Okay, let us assume length and breadth of a object. And there are two inequality constraints. So first inequality constraint says that x1 should be always less than x2. So only then we'll accept those values. Second inequality constraint says that x1 should be always greater than 10 number. Okay, so we have to satisfy these two constraints, inequality constraints. So let us plot these two regions. Okay, so first let us plot this. X1 should be less than or equal to x2, or in other words, x1 minus x2 should be less than or equal to 0. Okay. So what we do is that we plot this line x1 equal to x2 or x1 minus x2 is equal to 0. Okay, so this is the method for plotting inequality constraint. You first set it equal to 0 and draw that line. Okay, so this line x1 minus x2 is equal to 0 or x1 equal to x2 will divide the Cartesian plane into two halves, A and B. Okay, A is on this side, B is on this side. So on one side you will get x1 less than x2, other side you get x1 greater than x2. So you can find which side is which by sampling one point. Okay. Yeah, so we find that this is the side where x1 is less than x2. Okay. Okay, so this is the feasible region for this particular constraint. Okay, x1 is less than x2. Okay. Then one more constraint is that x1 is greater than or equal to 10. So that is drawn like this. So this is x1, this is the value 10. So this is the region where x1 is greater than 10. So this doesn't specify x2. X2 can have any values. You turn off your mic, okay? Okay.
പക്ഷെ വർക്കാവുന്നില്ല സം ഇഷ്യൂ ചാർജർ എന്തോ ചാർജ് പോയി വന്നു ഇരിക്കുക ഒരുപാട് നേരം വെച്ചിട്ട് ഇപ്പഴാ എട്ട് അല്ല എന്റെ ഫോണിന്റെ പ്രശ്നമാണെന്ന് അറിയില്ല ഇപ്പൊ പെട്ടെന്ന് വേണ്ടോ എനിക്ക് ചാർജർ വേണം
Okay, we'll continue the lecture. Okay. Oh, that what I've written is gone up to this slide. Okay. Okay, so we have plotted the two slides. Okay, the two constraints. Okay, the constraint 1 and constraint 2. So this is the feasible region or allowable region for constraint 1. This is the allowable region for constraint 2. So both have to be simultaneously satisfied. So you have to find the intersection of both constraints. So okay, let us plot intersection of both constraints. So it will be like this. Okay. So this region satisfies x1 is greater than 10 and this region satisfies x1 is less than x2. Okay. So this is the feasible region for this particular optimization problem. And any x1, x2 values here is acceptable. Okay. So that is the meaning of this inequality constraints. Okay. So next we'll tighten the constraints and make it more narrow. Feasible region will reduce it. How this is done is that one of the constraints we will make as an equality constraint. So previously we said x1 is less than or equal to x2. Now we will change it and say x1 should be equal to x2. So this is one equality constraint is introduced here. Other constraint is same. Okay, so if you do these things, you can see that feasible region is a line. So this is the line x1 equal to x2. So all the points must all the xy points must lie on this line, and this is the region which says that x1 is greater than 10. So if you want to satisfy both of this, only these points will satisfy both the conditions. That is, it has to lie on the line, and also x1 should be greater than 10. So you can see that equality constraints will drastically reduce the feasible region. So before you give equality constraints, you have to carefully think. And next we go to one third case, which is the very extreme case. Okay, so there the feasible region will vanish. So what we do is that we make both as equality constraints. Both as equality constraints. So x1 minus x2 equal to 0, x1 minus 10 is equal to 0. Now what we have is that we have two algebraic equations, okay? And you can solve it by drawing the two lines. So some algebraic equations are there. You solve it and I think you get x2 equal to 10 and x1 equal to 10. Okay. So what you get here is that, so with two design variables, we cannot have two equality constraints because it can be algebraically solved and there's no need for minimization or maximization. Okay. So with this, we can make the principle that is for n design variables, we can have only n minus 1 equality constraints. So if I have 5 design variable, then I can have only 4 equality constraints. Okay. Okay. So then only 5 minus 4 equal to 1. One variable will be left for optimization. Okay, so then another thing is there's no limit to the number of inequality constraints because each inequality constraint will only slightly decrease the feasible region. Okay, so you can have infinite number of inequality constraints and each inequality constraint will reduce the feasible region. So we can see here, suppose this is the XY plane. Okay. This is one inequality constraint, okay? So this side is allowed. Okay, then I draw another inequality constraint. Then I draw another inequality constraint. Then I draw another inequality constraint. Then another inequality constraint. Another inequality. So I can keep on drawing large number of inequality constraints and each inequality constraint will slightly reduce the feasible range. Okay, so there is no limit to number of inequality constraints. Okay, so that is the thing. I think we can stop here now. Okay, from tomorrow we'll go to the other topic. This is enough for introduction. Okay. Let me stop the PPT. Stop recording.